Today I have the pleasure of introducing Dr. Irvine-Fynn. He's a glaciologist at the Center for Glaciology, and I'm going to try and pronounce this correctly, but it's Welsh, so I'll do my best. Aberystwyth University in Wales. Since 2000, Tris has worked on glacier science in polar regions, and both in the Canadian and European high Arctic, with particular focus on hydrology research topics. In addition to high latitudes, Tris has worked in subarctic Scandinavia and Greenland, the European Alps, New Zealand's Southern Alps, the Argentine Patagonia, and the Nepali Himalaya. His research activities, while maintaining a process glaciology theme, bridged from geophysics to hydrochemistry and geomorphology to ecology. Tris joined Aberystwyth Centers for Glaciology in 2011 as a Climate Change Consortium of Wales Research Fellow, becoming senior lecturer in 2015, and he is currently working on a NERC-funded Black and Bloom project that seeks to explain the changing albedo of the Greenland ice sheet. I guess I didn't know this until recently, but he is one of our own here at University of Calgary, and he did his master's with Dr. Brian Moorman on something with ground-penetrating radar, and he won a Chancellor's Award or some very fancy thing. Anyway, with that, I introduced Tris, who's going to be talking about knowns and unknowns of supraglacial hydrology. Thank you.
Well, thanks very much for the introduction. Wasn't expecting that, so no, but thanks very much for that introduction, and hopefully the few of the things that I've got to just kind of present to you today bear a little bit of interest. So, as we said, the topic of the title and the talk is these unknowns and knowns of supraglacial hydrology, and supraglacial hydrology is an area that I'm becoming increasingly interested in, simply as I sort of move through a variety of the research projects that I've done, that actually there seems to be a lot of things that really we've made a huge number of assumptions about, and there's still a lot to understand, really, to sort of unpick a little bit more of what actually happens on glaciers. So the reason that this is important, is this now going to work? The reason this is important really actually ties into sort of the recognition that glaciers represent the world's largest freshwater ecosystem by a long way. And that freshwater ecosystem is very much a microbiological one, but essentially really what we need to recognise is actually that ice surfaces, melting ice surfaces in particular, really are a critical ecosystem and have a huge role to play in global biogeochemical cycling. So what I've done here really is just lay out a kind of a quick indication of where I want to take some of the information that hopefully I can impart to you today. So just really give you a very quick oversight as to glaciers as this ecosystem in their own right, and then touch on a little bit about the assumptions that we've made, simplifications and so on, and the reality of what glacier surfaces and particularly their hydrology is like. And then I'll focus a little on microbial transport, which is a project that I was involved with a couple of years back, exploring how quickly and how efficient the ice surface is at allowing microbes to move from on ice to off ice locations. And that really led into the next number of sort of topic areas, so thinking about near surface permeability and really kind of trying to get to grips with what's going on there, and looking at what we call microscale ponds, cryoconite holes as they're more commonly termed, as well as then moving and completely shifting out of any Arctic latitudes and taking us down to sort of more tropical latitudes, but looking at high altitude glaciers and thinking about mesoscale ponds and perhaps the role that they have in terms of dictating quirky hydrology on supraglacial runoff. So the final slide really is just to recognise how complex the system is and touch a little bit on what really we could learn from the periglacial literature. So supraglacial environments look like that. So that's an image from about 70 metres up, taken from a UAV, looking at a supraglacial melt stream. You've got a scale bar down there to give you an idea of the area that we're looking at. Kind of fairly complicated terrain. There's a lot of features on it, really highlighted just by the sort of the local shadowing. You can see the high areas, particularly a white ice. And this is taken from an on-ice location about 70 kilometres inland from Kangerlussuaq in western Greenland. So that's just kind of to give us an idea of the environment we're looking at and discussing today. So, turning back really to the ecosystem side of things, that supraglacial environment we just saw an image of, that really is a real large component of this supraglacial ecosystem. Now, supraglacial ecosystems has been a sort of concept that's been around for well over 100 years. Nordenskjöld described it back in the late 1800s when he was crossing Greenland, and so there was sort of indications then that there was some biology. There was a petrologist at that time, a guy called William Bailey, who then actually did some analysis of samples that Nordenskjöld took from the surface of the Greenland ice sheet and found a lot of organic materials. So the indication then was that this dust that had originally been seen on the ice surface that they thought was derived from the atmosphere or from space actually turned out to be more locally derived. So it was coming in, it was being blown in from any of the exposed rock near the ice margins, and it turns out that that had a lot of biological life within it. So in the early 1900s there was a little bit of research into that, but it never really grew a foothold, and it sort of just disappeared into the ether. In the late 1980s, there's a Japanese researcher in the Himalayas, Kashima, who really was looking at the little columbula that were found in these high elevation environments, and he discussed those and their life cycle as they moved up to the snow line and back on the ice, and tried to use them as an indicator of the fact that the ice surface was an ecosystem. However, again, that didn't really grow any foothold, but there was a very, very big review that was written in 2008 really referring to glacier ecosystems by Andy Hodson in the UK, and that's really sort of become the gold standard of our understanding of sort of where we got to and where we've built from since. And so his fundamental overview was looking at the glacier as a whole, so looking from the surface down to the bed and trying to understand really what was going on within that, identifying the fact that we have bacteria, microbes living at the surface of the ice. We found bacteria and microbes entombed in the ice. There's evidence from ice cores from Tibet that ice that's over 750,000 years old has microbes within it. So clearly there's a big cycle potentially to be played within the system. And then recent work has looked at increases in subglacial weathering as a consequence of the fact that you've got huge microbial populations at the ice bed interface. So this schematic really just sort of tries to emphasize that, but focuses mostly on the carbon cycle within there. Now, one of the more recent estimates that we've had a look at is taking some of the data from ice cores and trying to understand really what this ecosystem represents in terms of microbial populations. And the really most interesting component is looking actually at the top 2 meters. So if we take the top 2 meters of melting, seasonally melting glacier ice globally, excluding Antarctica, we actually find that we get up to around 10 to the 26 cells living within that 2 meter zone. Now, if we then compare that to the 10 to the 25 cells that we see in the top 200 meters of Earth's oceans, you kind of realise quite how busy ice surfaces are in terms of their microbial populations, their microbial dynamics, and the role that it has to play in terms of nutrient cycling. So, where that's gone is really there's been a focus on the carbon cycle. So there is some evidence that these microbes can act as nitrifiers at the surface, but a lot of those avenues haven't been fully explored yet. So the focus really has been on carbon, and there's been a slew of papers, and just this is a sort of snapshot of a couple of titles really emphasising the role that these microbes on glacier surfaces have in terms of essentially fluxes of carbon, drawdown of carbon, particularly from the atmosphere, and locking it up in terms of humic materials as these microbes kind of live through their life cycles. The fact that there is evidence of uptake in streams, obviously again this is related to the fact that an aquatic system is likely to be stocked full of microbes. And where this has then gone is to then look at, well, if they're in the stream, things are moving around, then there's got to be an export of carbon. There was some interesting work from the 70s in Glacier Bay in Alaska that actually found a huge spike in particulate organic carbon in the fjords close to glaciers that wasn't seen away from glacier catchments. But obviously, you know, the change in how we viewed particulate organic carbon has shifted slightly, and so we know what perhaps was a combination of what we now see today as traditional POC versus cellular carbon may be a little bit misleading. But nonetheless, what really has been sort of purported with a number of sort of high-profile papers is that there is this big release of both POC and DOC, so particulate and dissolved organic carbon, coming from glacier ice masses. So, A lot of the assumptions that are made, though, really come to sort of an offset phrase, which was kind of, if you like, emphasised in a sort of fundamental review paper of glacial hydrology from '98 by Fountain and Walder. Essentially, their argument was that the near surface doesn't really impart any delay in terms of the transit of meltwater off the ice. So they were assuming that once melt happens, then effectively there's a negligible time lag, if you like, between that melt being produced and exiting the glacier system. But obviously, when we think about that surface that we looked at before, this slide projector seems to be jumping ahead a bit. If we look at that surface that we saw before, yes, we've got clear evidence of streams and these moving into rills, but obviously there are large areas that don't seem to have any clear hydrologic systems set up on them. There's no obvious direct networks. And so the question then really does come to light, well, actually, when we look at this surface, do we really anticipate that melt from this position here reaches that stream with negligible delay or not? So, what do we know about these sort of systems? So one of the key foci of stream hydrology, certainly in the 70s, was really building on the geomorphic and civil engineering expertise that was coming out, particularly in America at the time. Really looked at meandering, trying to understand meandering, how these supraglacial streams develop these very sinuous pathways, and trying to ascertain whether that was related to something to do with the helical flow of the water, or whether there was other instabilities that sort of triggered that, and whether there were analogies between supraglacial environments, which are obviously more rapidly evolving than alluvial or bedrock systems, to try and see whether they could sort of fundamentally gain the associations between any of the driving factors and controlling factors. So there was lots of work that looked at variations in stream position and stream morphology, both in a sort of an up glacier sense. So this is, if you like, elevation, this is distance. So you've got the stream bed indicated as this sort of wiggly line with the trend lines plotted through. And there's been similar work trying to associate things like the meander wavelength, so the distance between, if you like, the sort of the peaks of the wave in the supraglacial system, to things like channel width and velocity and so on. So these are a lot of the knowns that we've got, and essentially from the 70s and early 80s, there hasn't really been much development beyond that. So there was some interest in looking at things like incision rates, so not only in terms of thinking about meandering in a lateral sense and the genesis of this wave-like morphology, but also thinking about whether, because you're on ice, which is very readily eroded by the water, we're looking at the incision rates. If you like, that's almost a meandering in the third dimension, so not only the lateral dimension, but you've actually got this third dimension, which allows for the incision. And some work done in the Juneau ice fields was looking at sort of characterising this and finding that actually what you could see was that because you've got such effective incision by stream water, so the flowing water itself, even at 0.01 degrees C, does allow for nearly 6 centimetres a day in terms of incision, so it's quite rapid because of the difference, the very, very narrow difference between frozen ice and just unfrozen water. And they found that you could plot through these little cuspate forms on channel walls, you could plot the daily incision rates. And this is looking at an example from the Greenland ice sheet. I don't know if it's quite clear enough given the lighting, but if you can see there's a number of very, very clear horizontal lines running on this stream bank, and essentially that reflects that same sort of daily incision on a supraglacial stream, that example being from Greenland. In addition to that, there was some recognition that glacier ice itself isn't a particularly homogeneous material, and there has a lot of structure in it. So if you imagine what happens, you have snow falling in the accumulation area year on year on year, that produces some sort of horizontal structure in the ice that's created. But as that horizontally structured material is moved or vectored down valley, oftentimes that valley will narrow from that wider accumulation area. And in terms of narrowing, that horizontal structure becomes folded. You're squeezing that horizontal structure perhaps through a narrower bedrock constriction, so that ice becomes folded. So that folding produces foliation, and you can see evidence of that looking here at, it gets very carried away this. Try again. So looking here, right, is there a keyboard here that I can use? Nope. Okay, got it, thank you. Right, I should just have to bounce back and forth. So you can see the sort of foliations there on the ice surface, and there are instances where perhaps the flow of the ice will actually cause multiple buckling and folding of those structures. And obviously when you start imposing those on hydrological flow, they may themselves have some controlling influence. So thinking particularly about the very, very linear foliations, streams can obviously occupy those, and you may find there are subtle differences in the sort of the resistance, if you like, that different ice types have, just because of the different crystal sizes, that allows those streams to then occupy a particular zone within those foliations and not elsewhere. So that kind of ice structure can be important in terms of dictating exactly where streams are, and in doing so, obviously that then eliminates lateral meandering, and so we end up finding that the meandering has to occur in the third dimension, which leads to these step pool sequences. So here we have a surface of the stream, and you can see three subtle breaks in the surface of the water, and those, if you zoom in, actually are related to very, very subtle cracks and fractures in the ice. So again, it comes back to the relative importance of structure. And importantly, when you see these sort of fractures in ice, that discontinuity can create a small step in the channel bed, and that small step essentially becomes a nick point, and that nick point, through thermal erosion, can start to migrate upstream, okay, as the transfer of energy occurs at that location. So although you may find, and you can spot step sequences associated with flow, oftentimes when you then look and you follow that upstream or downstream, you may find other steps which aren't clearly associated with those sort of structures. And there's been discussion of that in terms of what then can perhaps drive some of those. And the question is it always that structure leads to those sort of step sequences, or can those step sequences be generated inherently by the flow instability in the water? So a slightly older paper from the 90s that talked about the creation of standing waves. So that's essentially where you've got oscillations in flow which remain static over space and over time. And those roll waves within the water, obviously that leads to sort of pulsing amounts, if you imagine in space, it leads to pulsing delivery of energy to the stream bed. Okay, so you get different volumes of melting at different points in time. And Brian has recently looked at this and explored the fact that you can find pulsating flow, where you get, not only have you got this roll wave generating sort of slightly varying stream depth or channel widths as a consequence of this instability, but actually once you've got that, you may find that that inherently produces pulsating flow within the water. So this was an example where we're looking at a supraglacial stream here, and again, hard to see, but this is with it full of water, and a few seconds later, it's water free. So with water and water without, and that was literally over a course of a couple of seconds. So you see the water flow effectively turning on, turning off. These things have been observed, but obviously we still don't fully understand or recognise what initiated the topography in the first place, our sequence of steps and pools that really, if you like, kind of maintains this flow and amplifies it. So we can then look at the ice surface in a little bit more detail and think, well, actually, it's even more complicated than that. Here, we can see there's structure that trends sort of bottom left to top right, as well as structure that's going effectively directly up and down. In terms of scale, that's me lying down. So it's always useful to be your own scale in these sort of images. But then on top of that, you've also got the formation of streams that just seem to be flowing in a direction that doesn't clearly get governed by those sort of structural features. And as it transpires, if you look at this surface, the higher ground is here and the lower ground is over here. So your sort of elevation gradient, if you like, is from bottom right to top left. So again, the streams aren't necessarily directly following that gradient either. And a lot of that kind of uncertainty in terms of really what is driving a lot of these processes, what generates this kind of variability in supraglacial streams, has led to a sudden explosion in interest in supraglacial hydrology. So over the last few years, having had several decades of only maybe one or two papers coming through, there are a huge number that are starting to be produced now. So people have suddenly got re-energised about supraglacial hydrology. And sort of some examples of where this has started to move is towards these numerical simulations and looking at how streams are initiated, how they incise, how they develop, how they meander, and so on. And as I said, all of these just take sort of numerical first principle approaches. However, none of those really are tested yet. Okay, so there's relatively little data on supraglacial stream morphology and how that changes over time. But avenues that have started to present themselves as we've moved forward in terms of using structure from motion, photogrammetry as a way of retrieving 3D surfaces. We can take images of the surface and then construct a digital representation of that. And if we do that over time, that allows us to potentially look at our real development. And the resolution you can achieve is very, very much dependent on the camera you're using. And obviously the higher grade the camera you've got, the better the resolution you can achieve. But with a 5 megapixel camera, we can achieve sub 2 millimeter resolutions in the vertical and horizontal. Okay, so if you then anticipate, commercial cameras now, 20 megapixels is not uncommon. Mobile phones have got 40 megapixel cameras on them. Okay, so in terms of looking at that resolution over, and this is a plot area that's about 2 meters by 2 meters, but you can see the photogrammetric processing allows us to get a greater area, but the red pole here is about 1.5 meters tall. So there's an idea of scale. So using those sort of approaches, we might be able to understand a little bit more about how these systems develop, and that allows us to test some of those numerical models for stream development. Moving a scale up, this is using a UAV, flying at about 50 meters elevation, and trying to understand, again, looking at this sort of rill initiation and what drives supraglacial stream development and the network that's produced. So this plot here on the left is the reflectance, so essentially a proxy for albedo. And albedo is sort of the controlling variable when it comes to the surface energy balance. So any melt that we see on the surface is highly likely to be correlated to the albedo. So higher the albedo, lower the melt, lower the albedo, higher the melt. But we find that albedo also leads into variations in the melt rates, so that produces topography on the surface. So here we've got surface roughness, which is a sort of measure of how rough and undulating the surface is, and then comparing that to the drainage density, so the number of small channels and rills that there are. And there is some association between certainly the roughness and the channel density, as you'd expect, and some of that does crudely relate to the albedo, so the initial melt rates. And then going up a scale again, using sort of satellite imagery, people have been looking at that kind of thing rather than on a glacier scale, but looking at it at the Greenland margin scale. So here, this is Russell and Leverett Glacier near Kangerlussuaq, and they're trying to understand essentially the potential discharge, if you assume melt from this catchment area. They're trying to understand the potential discharge into moulins and crevasses that may then feed the subglacial system on the Greenland ice sheet. But all of the approaches here have assumed that we do still have this efficient transfer. And while it's true that we've got efficient transfer in the streams, what we don't really understand is the transfer away from the streams. So that sort of remains as an unknown. Now, where a lot of this has come through from is looking actually at geophysical surveys of ice masses, and particularly during the summer months, and looking at temporal changes during the summer when the melt season is in progress. Early on in the melt season, this is looking at the surface, so only looking at sort of 10, 20 meters or so in terms of depth here, but you've just got a very clear ground wave and the reflection that comes from the ice surface itself, with a little bit of noise, but not a huge amount of noise underlying that. So this is on a polythermal glacier where you've got cold ice below. So here the interpretation is you've obviously just got the ice surface, there's perhaps a little tiny bit of water at the surface as you'd expect at the start of the melt season, but there's very, very little interstitial water at depth because the ice is still cold. Later on in the season, exactly the same area, same sort of radar profiles we've got, but you can see here we've got a huge increase in the amount of noise that's in the radargram there. and that is linked to an increase in the volume of water close to the surface. The noise itself is obviously going to relate to just the presence of water, so it doesn't necessarily mean that the water is extending 20 metres or so below the surface, because you get a lot of interference and multiple refractions from any of that near surface water itself. So, but the interpretation there is that you've got an increase in water content at the near surface. So, this is starting to get a little bit annoying. So, try again. Stay. Okay, so looking at this increase in water volume, we ask ourselves what's that related to? And essentially that's related critically to the ice temperature. So looking at temperature profiles, and each of these lines are for individual months, so they're the mean temperature at various positions with depth away from the surface, here at 0. We're looking at these monthly means and the monthly gradients of temperatures. What we see is in July and August during the melt season, this is some data taken from a glacier in Svalbard. So in July and August, our summer season, we find that the top metre or so of ice tends to 0 degrees. So it's at melting point, okay? But it's not a melting point at the rest of the year. So what we'd expect in July and August, as we've seen in the radar, we would expect some melting to be going on, and some of that melt may start to filter through the interstitial spaces, the veins between each of the ice crystals, and so we'd expect a slight increase in water content in that upper metre or so. Okay. And really that leads back to, it's a much older paper by Muller and Keeler that was really done up in the Canadian Arctic, where they introduced this term weathering crust for glacier surfaces. What they said was that when you look at the glacier surface, the melt obviously isn't uniform, and because ice itself is partially transparent, some of the incoming shortwave radiation energy passes through the absolute surface, will pass into the subsurface, and you can get subsurface melting, perhaps where that radiation is interacting with the crystal boundaries. So as a consequence, over time you see the top, up to a metre or so of ice can start to degrade, and the crystal boundaries start to melt, and essentially we lose, or we drop our bulk density. So all the ice density stays the same because you're melting the crystal boundaries, you're increasing the amount of void space, and we drop our bulk density. And the water that's produced obviously then is driven by gravity, so will descend to the lowest position it's able to. In cold glacier ice, so in particularly polythermal glaciers and those that you see more commonly in the Arctic, the lower boundary is going to be limited by Beer's law. So Beer's law is the depth to which solar radiation can penetrate through ice. It's just a function of sort of the crystal sizes, the impurity contents and so on. But that gives you essentially a thermal limit to where water can potentially exist or drain. On temperate ice, it's a little bit more complicated. So temperate ice is where the glacier ice is close to or is at the pressure melting point throughout. And that lower boundary is far more elusive to understand, because you have to take into consideration capillary action, which is the draw up of water as a consequence of changes in air temperatures. Okay. So in temperate ice, it's a lot more complicated, but it becomes a sort of hydrological limit rather than a thermal limit. But either way, you do have this sort of limit posed, and so you end up with this perched aquifer, or sort of a water table within our weathering crust. And that weathering crust itself, that zone, extending maybe a metre or so in terms of depth, that can actually allow for water storage of around a centimetre a day. So in terms of air, it's the volume of water that could melt and essentially be stored in a lot of those cavity spaces that are created within the weathering crust. Now, if we've got this kind of porous media at the surface, and we've got complicated flow and we've got the potential for storage and release, what does that do to our runoff? Remember, we're all thinking that this is all efficient, and the melt should be reaching the streams without any lag. So looking at some work Scott Munro did on Pato Glacier, he looked at some simulations where he had the modelled melt, which is in the solid black lines, and then he had the observed runoff from a small supraglacial catchment in the dashed lines. And you can see in this upper plot, for one period of time he had, rephrase, it's the melt and the runoff. My fault. 1971 and 2008. So there are two series. The top one is the amount of energy. So solid is 1971, dashed is 2008, and the lower plot is the melt volume in 1971 and 2008. And so what he found there was in 71, there was a very nice close correlation between melt production and runoff, but in 2008 he found there was this huge lag. So up to 11-hour lag between melt production and runoff peak. So, looking at that a little bit more closely, we can see that that's not very efficient. And have we got more evidence for this idea of it not being that efficient? So this is the project I mentioned earlier, which was to look at whether or not microbes were transferred through this weathering crust efficiently or quickly. And so we took a glacier in Svalbard, Middle Irvine-Fynn, which is, stars move, it's up here, and we had this supraglacial catchment, closed supraglacial catchment, and we had a number of monitoring stations throughout it, and we monitored the outflow from it. So we looked at ablation, we took some ice cores, we looked at the volume of, the amount of dust that was delivered, and tried to understand the sort of budget of the small-scale particulates. And we measured those using flow cytometry. When we came up with a plot, this is looking at discharge with the particle concentration. So this is in the black squares, we've got the total number of particles, and then those that we can discriminate into something that was biological, so effectively it had DNA in it or on it. We then had cells, which were clearly defined by their size, and then we had the non-cellular material, so if you like, the non-cellular would be things like broken cells, remnants of cells, bits of plant, that kind of stuff. And essentially, if you add non-cellular and cellular together, you end up with the biological. Now, what was really interesting with this was seeing this non-linear trend, right? So you'd anticipate that as you get more melt, obviously you're melting stuff, there's more water around, so you'd think you'd be flushing more of the microbes out of the system, okay? But that wasn't the case. So the non-linear trend was interesting. So the question then came down to, have we got, right, apologies for this, every time I'm touching it, it seems to do things that I don't want it to do. So, have we got cell mobility that's being heightened at these low melt rates? So essentially, rather than having some sort of linear transfer as water volume increases, cell numbers decrease, or have we got something that suggests that actually what happens is as the melt's progressing, we get a dilution effect. So more water's being produced, and it's diluting the number of cells. Well, when we look at the ice cores, now it's not going to do it, is it? When we look at the ice core concentrations of cells, that's the average concentration of cells in the top metre or so of the glacier ice within that closed catchment. And essentially that's above anything we saw in the stream. Right? So if that's the case, we've got more cells in the ice that is melting than get released. So there has to be storage. So we can discount the idea that we've got heightened melt rates at low discharges, because we haven't. Right? We've still got less cells being produced than the amount of water that's being produced. And at the top end, when we've got high discharges, if we've got high discharges, we haven't really got a dilution. There must be something else going on, because if what we're melting has that number of cells in, where are the cells going? So there's an offset in the budget there. So we can discount both of those. Right, you have to forgive me, I do apologise, it's just misbehaving. So, when we look at it in terms of a budget though, we can look at what came into that closed catchment and what left, and essentially that's looking at what's released to the down valley environments. This is a little table of those sort of results from that study. So we were looking at sort of around 10 to the 16 cells, which when you do some equivalent calculations, you can work out that in terms of tons of carbon per year, tons of nitrogen a year, tons of DNA a year that get delivered to those downstream ecosystems. We can then multiply that up if you do some quite horrendous back of the envelope calculations, but we can multiply that up, and we get around 10 to the 21 cells based on that study for that small supraglacial catchment. When we look at global estimates that have been made, we're in the same orders of magnitude. So that's kind of positive that people have looked at that, but they've made those assessments just off ice core records rather than anything beyond. So we're looking at actually monitoring, counting the cells and getting a value of 10 to 21, and that actually does sort of aligns quite well to the global estimates. But as we saw, the transfer process was inefficient. So as we got more melt flowing through the system, we actually had a decrease in the number of microbes being liberated. So that has to mean we had storage. So if we've got storage, when we look at it in terms of our small catchment, actually we had around 22 kilos of carbon stored just over the course of the summer. And that's stored in terms of cells, humics, and so on. Right? So the ice surface itself acts very much, or seems to act, like a giant filter. Yep. And the reason that it does that is because when you look at what happens within those ice crystals, and as those ice crystals melt, and you have the little veins enlarging, those veins are the same size as little microbes. So these are the veins, and these are some silica spheres, which are a mean size of a typical cyanobacteria. And you can see that when you look at it under electron microscope, you can see all the spheres nicely aligning in one of the interstitial spaces. Okay? So more evidence that our surface ice acts like a sort of giant filter, and then effectively the permeability of that broken up ice is quite important. So the next step really was to try and understand really what's going on with the permeability. And so I built some capacitance probes that allow us to measure recharge rates. So that's borrowing from groundwater hydrology, borrowing the sort of techniques there. So drilling small boreholes, pumping the water out, putting the probe in, capacitance probe, which then allows us to measure the rate at which the water returns to that hole. And from the rate at which the water rises in our little boreholes, we can get permeability, we can calculate permeability. So we did some experiments on glaciers from the Alps, through Scandinavia, Greenland, on Bylot and in Svalbard, and just plotted up a few simple graphics here. So we're looking at the permeability relative to latitude, because obviously you'd anticipate that at higher latitudes, your sort of melt efficiency is less, air temperatures are lower, shortwave radiation is less than it is at lower latitudes because of the sun position. So we might expect our weathering crust to be more developed at lower latitudes, and so our permeability would be higher. But in fact, we don't see that, and the pattern between permeability and latitude is a little bit confusing, particularly here where there seems to be a trend, but then the final set of data from Svalbard sort of, if you like, disproves that. We can have a look at whether the permeability relates to the sort of receipt of shortwave radiation since the end of the winter season, so since the sort of the mean annual or the mean daily temperatures are above zero. And again, we can see that there's no real pattern there at all. And when we look at that in terms of instantaneous melt rate, so that's looking at the permeability based on how quickly melt is occurring at the time, again, no pattern. So permeability just seems to be incredibly confusing, but there seems to be an enormous range. So all of the sites showed a huge range in permeability. And what that permeability ranged between was between about 1 millimetre in terms of lateral movement that the water can make per day through to around 10 metres. Okay, so we've got a massive range in how quickly water in that weathering crust can move. One of the reasons that we think is behind that is back to ice structure, but it's to do at the crystal scale. So when we compare ice crystals, this is from Storglaciaren, so it's just two random points taking ice crystal samples on Storglaciaren. You can see the difference. This is a carpenter's rule, so about 25 centimetres, and you can see the differences in crystal size. Okay, so when you think about different crystal sizes, you think about how many void spaces a small crystal area is going to have versus the amount of void space that the large crystal area is going to have. That's obviously limiting the number of flow paths that are potentially viable through that, and that will in turn influence your permeability. So in addition to that, we thought, well, what would be interesting to see is there any variations in that permeability or in that water table that relates to that melt process. So we put some of these probes in at fixed positions. We corrected for the melt. So we drilled the holes in and then we looked and corrected for the observed melt over time. And what we have here is we've got an array of probes, and this is over the course of 7 days. And this is the water table height, so the height at which that water is within the weathering crust, measured from the bottom of a 36 centimetre hole. So if you like, this 36 upper boundary is the ice surface. As I said, it's been corrected for surface lowering. So what we can see is there is a slight trend of a decrease in the water table height followed by an increase. But superimposed on this, in the middle of each day, you can see the melt process. That's when we expect most of the melt. When the sun's at its highest, air temperature is the highest, we can see that the water table rises. So that's quite an interesting sort of observation, and clearly demonstrates that what we've got occurring is when we produce our melt, it's draining into the weathering crust, and then it must be moving from the weathering crust, right? So even though we've got low permeability, the question comes, how do we end up with supraglacial streams responding usually so quickly, and that assumption of very, very limited lag time? And the only route we've thought about is, again, turning back to groundwater and thinking of piston flow, that essentially if you imagine water being produced at one point on the ice, it's very, very low permeability, but that water's going into the weathering crust, and it must be displacing water that's right close to the stream. That's the only way we can envisage moving the water through and allowing the streams to respond very quickly, because it's not clear that even when the water table rises, that suddenly you have an increase in the permeability and the sort of rate of flow that new water, if you like, can run off the surface of the water table to the stream. So we then thought, well, we'll have a look at the surface in a different way and see if we see the same thing. So on a lot of glaciers, you find features called cryoconite holes, and they are sort of dark dust and humic materials that typically bind together through the active microbiology that's there, and through the difference in their albedo. Because it's darker, it absorbs more heat, and so it melts in, so it drills these little cryoconite holes. And these themselves have obviously got water within them, again being sort of, if you like, part and parcel of this weathering crust. So we instrumented up these cryoconite holes on a glacier in Svalbard, and just had an array of them close to a stream. And this graph shows, on the top side, it shows shortwave radiation, I star, and air temperature, so we can see the clear diurnal cycles as we'd expect in terms of sort of your normal meteorology for a day. And then the lower one shows, on the top part of the plot, it shows the water table position, essentially this or water table, or the cryoconite volume, water volume, which essentially is a proxy for the water table position, and the melt rates in the black at the bottom. We can see that over time we saw that the volume in the cryoconite holes decreased, but the variability of those volumes increased. So there was a sort of clear transition as we started monitoring these in terms of the amount of water that was being stored and then released from the cryoconite holes themselves. Superimposed on that, though, we did see on some of the holes, these little red triangles are sudden drainage events. So you'd have the cryoconite hole and its water table would be fluctuating on a daily basis, but it would then suddenly drain. And we think the sudden drainage events are through thermal stresses, because obviously you've got a melting ice surface and you've got cold ice underlying it, so you've got quite a big temperature gradient over only a meter's worth of vertical space. And that temperature gradient can be enough to trigger slight fracturing, small-scale fracturing in the ice. And those then lead to these sudden drainage events where one of these holes is connected to one of these fractures and the water is able to escape. But even more interestingly, when we look at our pattern of melt and we look at our pattern of water volume change, we see completely the opposite to what we saw in the weathering crust itself. So we see the water volume increasing, so essentially the water table is rising when we've got minimum melt occurring. Okay? So in the weathering crust, our water table seems to rise as we get melt and fall in the night time when we don't have melt. But when we look at the cryoconite holes, we seem to be out of phase with that actually the cryoconite hole water volume increases i.e. the water table rises at night and falls during the day. And as yet, we have to resolve that, but again, it comes to these ideas as to whether there's this translation between the water that's in the weathering crust to the holes. So the water's filling up the weathering crust, but we've got low permeability, so it takes some time for that water to reach the holes. So that's the only way we can try and explain that out-of-phase patterning. So, moving on, and hopefully, and I apologise, I'll probably go on for about 5 minutes longer than I'm supposed to, but hopefully that's okay. So, one of the further lines of evidence for a sort of an absence of very permeable near-surface ice is the creation of supraglacial lakes. And that's most explicitly and sort of more evidently described on Greenland particularly. So this is flying over the Greenland ice sheet in a mainstream airliner. You can spot these lakes forming. And this is one of the satellite images from NASA with the scale bar 6 kilometres. Gives you an indication of how prevalent these supraglacial lakes are. So again, it kind of highlights the fact that supraglacial hydrology is not fairly straightforward. You know, there's a lot of these storage processes going on, not only in the weathering crust, but as well as due to the fact the weathering crust has limited permeability, that allows these lakes to develop in any areas that are topographic lows. So in Greenland, that's been really, really important to think about these lakes, the fact that they build up. There's then sufficient water volume to cause hydrofracture, which can allow that water to escape to depth, or potentially even to the ice sheet bed in Greenland, in cases where you've got either sufficient water volume in the pond to start with, or you've got continued water provision to that pond location once the fracture opens up. But one area that hasn't been sort of thoroughly explored and is starting to become an area of interest is the Himalayas. And the reason we sort of talk about the Himalayas is because debris-covered glaciers are very, very common in the Himalayas. So around 30% of Himalayan glaciers have debris-covered lower elevations, they're termini. And that debris cover itself, through the function of differential albedo, through the function of differential debris thicknesses, leads to differential melt rates. And those differential melt rates lead to increased topography of the surface. So this is Khumbu Glacier, and the outline of the glacier here is this ridge line, and that sort of very, very pockmarked rough zone in the middle, that actually is the glacier surface. And if you zoom in to that glacier surface, you can see a number of ponds scattered all over it. The reason people are suddenly interested in these supraglacial ponds is it seems that these supraglacial ponds are the driving force behind the rapid thinning that we're seeing on Himalayan glaciers. So, kind of on a sort of global average, you'd expect most mass balance surveys to suggest around 30 centimetres a year is where we're getting to in terms of thinning rates in some of these locations. If we're looking at kind of magnitudes of thinning of that rate, we need to explain how that's happening. When you look at a surface like this that's covered in debris, you would anticipate that the debris would shield the underlying ice from melt. Okay? And that's certainly the case once you get above a few centimetres of debris. Okay? When you've only got a very thin amount of debris, perhaps maybe up to a centimetre, that debris can warm up and it'll melt the underlying ice in the same way that we see the dust form in the cryoconite holes. But the moment you start increasing the amount of debris, increasing the volume of debris, increasing the debris thickness, that debris acts as an insulator. So the question then comes to, why do we see such rapid thinning rates on debris-covered glaciers that should otherwise be insulated? And the reason is these ponds. Because you get differential melting, you create the ponds have got high thermal capacity, so they warm up and cool down slower, and they can effectively drill into the ice, a little like the cryoconite holes, just in the absence of the debris at the bottom of them. And obviously in drilling into the ice, the moment they drill into the ice, they expose glacier ice on their flanks, and that's then subject to typical melt processes, air temperature, instant radiation, and the ponds widen. So when you average that out over space, the thinning rate of the glacier is enhanced. So there is evidence that the number of ponds on a lot of these glaciers, and this is Khumbu Glacier, so the same one we see here in the imagery, that these ponds are increasing in terms of their number and connectivity. But we don't know a huge amount, and trying to understand how they connect is very, very challenging. So one of the other projects that I've been involved with was looking at this supraglacial hydrology, so a quick map of the area, that essentially there was only one stream flowing from Cumbre Glacier that came from an outlet lake here at its lowest most point, and this whole area mapped through here, this is all debris covered, so you can see that through satellite imagery there. So we monitored the outflow from there, and we found, sorry, this really is frustrating, and we found, you know, the air temperature as we'd expect, seasonally increased and then decreased. We found the debris temperature took a long time to warm up, but then increased, and as soon as the air temperature started to dip below zero again, debris temperature then returned to zero, and sort of clearly the debris had frozen up. This just gives an indication of what the potential radiation is, so we've got an idea of how much sunlight we might have received. This is our hydrograph, and we can see we've got, as we'd expect in any glacial environment, during the summer season, you expect an increase in the discharge and the amplitude, diurnal amplitude of that discharge, and then it tails off as the air temperatures fall as well. We then looked at the hydrograph itself in some detail, and we looked at the recession curves from the hydrograph, and we found that there were three components, so two of which were very closely aligned and were statistically the same, and one that was substantially different. Those three curves are kind of illustrated in this red sort of symbolic plot here, and we found that the two that were the same were the recession from the peak flow and the base flow, and the one that was very, very different and showed a sort of more seasonal trend with change was this sort of major recession that occurred. When we compare that to a typical glacial recession, we see a very, very different form. So typically, a glacial recession would see a rapid drop-off in terms of the discharge, which is, if you like, the surface melt, and you then move to sort of englacial or subglacial drainage and then a base flow. We certainly didn't see that. So, as a consequence, we looked at our outflow, which was fed by our lake, and we came up with this kind of conceptual plot of what we think was going on. That essentially, very much like we see with the weathering crust, as the summer developed, the debris layer that we see thaws out, okay? So then becomes potentially more hydraulically transmissive. As it becomes more hydraulically transmissive, water is able to feed from higher locations and the snowmelt that's up glacier through the system and start storing itself in the ponds. So these are very much like giant cryoconite holes, and so these fill up, and as they fill up, obviously they start to deepen, and our debris becomes completely thawed. And then as we move into sort of the end of the summer, as the air temperatures drop, what we see is that because we're on ice, we have the freeze up of the debris at that debris ice interface, but we also have freeze up of the debris from the atmosphere downwards, and so end up with only a smaller zone of thawed pathway to join up the ponds. Those ponds in turn start to drain as and where they can, but essentially the system then totally freezes up again. So if you like, here we're looking at our debris layer very much in the same way that we're looking at our weathering crust. That essentially the permeability has to change over time based on the energy that it receives. So that's kind of the end of what I had to say. And really, I guess what I've tried to demonstrate is that the glacier surface hydrology really is more complicated than has been appreciated up until now. And there are a number of unknowns that we've still got to look to answer. So particularly thinking about the sort of the thermal erosion of supraglacial streams, so how efficient are supraglacial streams at meandering, creating these step pool sequences, how quickly can they develop? Are incision rates capable of entombing supraglacial streams, you know, after perhaps a decade into an englacial environment? That effectively they are slowly incising down, becoming englacial or even subglacial pathways. There's clearly something that we need to understand about the ice structure and characteristics, the hydraulic characteristics. So what controls do ice structure have on that, and does that have a big influence on the hydrology and the rate at which water is essentially able to escape from the glacier? There's a lot of questions about heat transfer processes, not only in the ice, but now, as we saw in the last case study, for debris cover as well, which as yet aren't very well explained, certainly in the glaciological world. We still don't really understand the regulation, the porous media that either the weathering crust or the debris cover plays. We don't really understand the regulation role that has in terms of dictating runoff. And we really don't yet understand anything about how those hydrology characteristics dictate our fluxes of carbon to fjords or the oceans. However, there is a common theme here, which is where I'm grateful for my time here as a graduate student, learning a bit more about permafrost. Really, I think there's an awful lot we as glaciologists have to learn by consulting the geochronology literature and understanding particularly the active layer characteristics. And when you think back to ice temperatures and so on, I'm sure you've all seen plots of active layer temperatures that look very, very similar. So I think, starting to look at glacier surfaces as an analogy to permafrost active layers is a really, really important step to make. And if you like, that's my kind of going home point. So hopefully, thanks very much. Thanks for listening. I hope that was vaguely informative. There's a slew of thanks to various funders that I should sort of make, but otherwise I'm open for any questions.
Your ponds on the recovered glacier.
Yep.
In the mid-monsoon season there, when we fill up, do you see any examples of them actually topping over and forming channels from one pond to the next?
No, I haven't. That's not to say there isn't examples of that. It's the surface of the glacier, as you probably appreciate from the imagery, is incredibly difficult to navigate around. And I think the magnitude of heights that you're looking at suggests that may not be the case. However, there is evidence of what looks like hydraulically exploited fractures that perhaps have had a small tunnel that have somehow linked one area to another area. And there's been some speleological investigations that have done that, so on ropes and climbing in and around, that have sort of shown that there are bits of pathways that seem to suggest that at certain times there may be lakes that can connect to others. But otherwise it seems that quite a lot of the connections are either hidden, essentially you've got a lot of slumped debris, or it's debris that's in situ and the hydrological flow is somewhere below that surface.
You can see that as you sort of go, as it fills up more, the blocks are getting bigger towards the surface. There's flow, it's just that it's hidden underneath the rubble.
That same topic. So, if there's certain pathways in these lakes, I'm assuming that's where the melt is concentrated?
Yeah, so, well, yes, theoretically. So if that flow is transferring across the ice interface, then absolutely, then you'd expect there to be some melt genesis there, yes. But we don't know necessarily where it is. So it could be that if you've got a lot of the sands and clays, it might be that actually it doesn't quite reach that ice interface. But again, it's unknowns. And so the debris cover on Khumbu, up near Everest Base Camp, it's the order of a couple of centimetres. But there's some radar studies that suggest that it's between 2 and there are some bits that they think maybe 14 metres of debris. And so trying to even approach the digging through to see where it is hasn't yet been done. However, what there is happening next year, there's a project that was nicknamed Neverdrill because no one thought it would ever happen, but it's called Everdrill, and they're looking at sinking a number of boreholes through the debris layer and to the glacier bed. So they've got a 9-week field campaign next April.
Any other questions? All right. Tris, another round of applause.
Thank you.